All right, so before I start diving into ionic solids, I just want to kind of refresh where we have been so far. So the first thing we were talking about was just the classification of our four different types of solids. Remember, that classification is really important because if you misclassify, it doesn't matter how beautiful your answer is, it's all going to get marked wrong. So you really need to get that first step right. And what I want to show you is this summary table. So if you guys remember, the four different types of solids were the metallic solids, the ionic, the covalent molecular, and the last one was covalent network. We've talked about different ways of how we identify each one. We have done the metals in detail now, and you guys have some specific notes on metals, and we talked about some of their properties. So let's just find that. That was in the next lesson. It's so good that you have a website. Websites are the way to go. So we talked about metals as our last kind of main lesson, and we talked about how they are structurally. That structural formula is really, not structural formula, that structural setup is really important because that's going to then lend it to have specific properties. So with metals, we talked about how it has the positively charged nucleus or nuclei, because we're talking plural, and all the delocalized valence electrons that are kind of spinning around and kind of moving wherever they want. And that's going to lend to the properties that metals have, such as malleability and their charge and things like that. So we've done metals. So like I said, talking about what they're made up of, atoms as their particle, and the bond that holds these guys together are metallic bonds. When you guys go to justify their property, you're going to be using a combination of what the particle is and its structure, and then the bond that is holding that structure together, depending on what property you're talking about. So like I said, we looked at it, looking at their malleability and how they have that ability to change without breaking, but they have that strong metallic bond, making it a high melting point and making it insoluble in water. So that's kind of the crash course in what we were talking about with the metallic solids. Now what we're going to be looking on to is the ionic solids. So these guys here have lots of particular properties. When we are looking at metallic solids, I'm just going to spotlight this. There we go. So when we are looking at metallic solids, what you are looking at is a set kind of ratio between the positive cation and the negative anion. In this case, it is sodium chloride, and we see that sodium has lost one electron to go down a valence shell and to become stable. And because it's lost that one electron, it needs to go somewhere. So it's gone to that chlorine atom. It has gained the one electron to complete its electron shell, and it has now a negative charge because of that disbalance between the protons and the protons and the electrons. Are we okay with that so far? So when we are thinking about what particle makes them up, the particle that makes them up are the ions. So that's the slight difference now. So we have to be really careful with the terminology. The second thing to keep in mind when we're talking about the ionic solids is that this electron transfer is not the bond. It's the electrostatic attraction between that positive and negative charge. So that's what's actually holding the ionic solid together and making that ionic bond. So keep that in mind. It's not the electron transfer that's the bond. It's just the resulting factor that something is positive and the other thing is negative, and thus positive and negative attract, and then they hold together. This one here is just an example of something that's like a 1-to-1 ratio, but if you had another ionic solid that had like a 2-to-1 ratio, it would be a similar sort of setup with a very set lattice. So something that's different from metals compared to ionic solids is that this lattice is set. It has to have a certain structure. And so in this structure, it's going to be alternating that positive and negative charge. That's going to change the properties of the ionic solids compared to that metal. Are we okay with that so far? All right, keep going. I'm not really sure actually how much notes I'm going to be writing down because a lot of it's just going to be shown visually. But if you want me to write something down, let me know. All right, so when we are thinking about ionic solids, actually I will write some stuff down and I'll compare it against what I wrote down for the metals. So, trying to see what I have down here. Actually, I should grab my notes from the other day so that way we can actually compare it. Come on, open up. There we go. Oh, there it is. Just want to make sure we have similar notes. Okay. So, some things to kind of note with ionic solids. So their particles, you guys remember, are the ions. And the force holding it together is the ionic bond. Now be mindful that that ionic bond is the result of the electrostatic attraction between cation and anion. Yes. Let me double check. Yes. And just as a little reminder that positive and negative anion cation is formed when the ion forms. Potentially S, depending. Electrons. You guys are going to learn a lot of my shorthand. I don't like to write. Are you okay with that so far? Okay. Something, like I said, is unique to the ionic solids compared to the metals is that this does have a set 3D lattice. So what that means is that it has a set particular structure. It's not just random. That particular structure. So just as a comparison to what we were talking about last topic, I'm just going to quickly put something down. So when we talked about metals, we said that they had no set 3D lattice. So with that no set 3D lattice, it was because the electrons were delocalized and they were moving everywhere around. There wasn't a set bonding pattern between this nucleus and that electron. So that had no set 3D lattice. This one does have a set 3D lattice. So we have to have that alternation between positive and negative. Should have probably done that in 2 different colors, but a little late now. So we see whether I'm drawing the structure, we have positive, then negative, positive, then negative, negative, then positive, negative, then positive. So when I look at something that's negative here, you see that everything that's surrounding it is positive. When we look at something that's positive, everything around it is negative. So that's that set structure. So it needs to be in that pattern. If it's not in that pattern, we're going to get problems. And that's why it's going to have certain properties. Are we okay with that so far? Hopefully this makes sense from the pre-learning you guys were doing. Cool. All right, one of the things we talked about with the metals was malleability. What does malleability mean? It can be molded, so we can change shape. So if I hit, say, for example, a piece of metal with a hammer, it will change shape. Will it break? No. So it's able to adapt. If I had a little salt crystal, and some of you guys might have done this at home, and you smash it in like a mortar or pestle, what happens? It breaks and it gets really fine. You even see that when you have like your normal like salt grinder. So let's say you have those big giant crystals of salt in a salt grinder, and then you grind it up so that way you don't get giant chunks of salt in your food. So you get like freshly ground salt. So that reason why those two solids behave differently ties back to their atomic structure and what's going on at the particle level. So when we're thinking about ionic solids, they are brittle. And the reason why they are brittle is because, that's not what I want to do, but that's closer. Spotlight, there we go. So here is an example of my ionic structure. Let's say the positives are the green. let's say the green is going to be the positively charged cations and the orange is the negatively charged anions. So this is showing the set 3D lattice. We have that alternation between positive and negative. And let's say I want to apply a force to that ionic solid and I want to try to change its shape. So I smash it with a hammer. When I do that, I force the ions to move, but when I do that, I'm going to get an alignment now of like charges. So we're going to get positive charges next to positive charges, negative charges next to negative charges, and what happens when like charges are next to each other? They repel. So since they repel, they're going to break apart. So that's why when we're comparing between ionic solids and metallic solids, that's why one is malleable, but the other is brittle. Are we good so far with that? So that was one thing that we talked about in that. These guys will also have high melting and boiling points. In fact, a lot of the ionic solids tend to have higher melting and boiling points than the a lot of the ionic solids tend to have higher melting and boiling points than metallic solids, and that's because the ionic bond is stronger than the metallic bond. So when you're looking through, you should expect ionic solids to also have high melting point, high boiling point. Are you okay with that so far? So that kind of covers the first two ideas. Melting point and brittleness. The other thing we need to think about then for their structure is their solubility. So when you put metal into water, does the metal dissolve? No, it shouldn't, or otherwise you've got a real big problem. And the reason for that is because that metallic bond, it's strong, and the attraction to the water is less than the attraction to itself. So it's more attracted to itself than it is to the water, so it won't dissolve. In this case, with ionic solids, they can be soluble in water. And let me show you kind of why that is the case. I do have a video that I'll play. I turned off the sound because it actually doesn't have any sound, and I'll talk you guys through it. So a lot of these things help with visualization. All right, so this is just normal table salt dissolving in water. So here is a water molecule. And you can see that it is next to a salt crystal, which is sodium chloride. All right, so I'll just pause it right here. So one of the things we need to think about when it comes to solubility has to do with what you are dissolving items into. And in this case, you guys did a practical the other week, and you had water, you had ethanol, and then you also had just like normal cooking oil. Now, the solubility of things will depend on what the solvent is and whether or not that solvent is polar or non-polar. Water is an example of something that is polar. And some of you guys have hopefully got onto this when you're looking at the covalent molecules, is that there can be an unequal sharing of electrons, resulting in an unequal distribution of charge. So right now in my water molecule, we have oxygen over here and then two hydrogen atoms over here. They have a covalent bond, which means they are sharing electrons to get their full shells. Now, in this case, the oxygen's more electron negative than the hydrogen. So it's going to pull those electrons like a tug of war closer to it. Since it's pulling it, but not fully taking it away, it becomes slightly negatively charged. So it's kind of like when an ion forms, but it's not a full ion because it hasn't lost the electron completely. In this case, because I now have lost those electrons and those electrons aren't nearby me, my hydrogen section becomes slightly positive. So that's what we're looking at for the polarity of the water molecule. So water is a very polar molecule. Do you guys want to just see how this is dissolving, and then I'll talk about the other two substances. So that's what's going on there. All right, next thing we're looking at is, let me get you know. All right, so next thing that's going on is we have the salt molecule. And the salt has a positive cation and a negative anion. So in this case, you see it's starting to pull things away. I'm trying to find my notes. And again, it's starting to pull things away. I'm just going to pause it here. Please finish the notes. Yeah. Let me just finish explaining this, and then I'll write a note. So what you see here is you have the two ions that make up salt. This one here would be the chloride, so that's the negative ion, and then this is going to be the nitrogen, which is the positive ion. You see how the water molecules are flipped around? So in this case, the water molecule, the slightly positive side, has surrounded the chloride, and then in this case here, the sodium, that's the positive ion, you have the oxygen end of the water molecule, which is slightly negative, surrounding it and isolating it. So because it's able to isolate it, it's able to pull it apart. So that's how you see, that's what basically is happening at the molecular level for dissolving. Let me just write this note, and I'll play that again. And that's how things dissolve. All right. Dissolve the earth. All right, I'll just show this again. Oops, sorry. Well, there. Okay. So, like I said, we were talking about the sodium ion being positive and the chloride ion being negative. And then once again, you see how the little water molecules are surrounding it and pulling it out. And again, it has to do with that positive-negative attraction, pulling it out. So that's how that's dissolving. All right. So let me just finish writing these notes because people need to go to the bathroom and stuff. Savannah? No, you can go down. She's going to the nurse. There you go. All right, so let me just kind of draw that so you guys can think about that. I know it's raining. Huh? Those ones aren't open yet. I think they're still working on the plumbing. All right, so let me actually do this nicely so you can actually have more colors. All right, so that, for example, is my ionic solid, and I have a water molecule that's coming by. It's not worth the rain. So if a water molecule comes by, what's going to happen is I'm going to have H2O. It's like Mickey Mouse. And what's going to happen is the slightly negative ends of that water molecule is going to surround that positive ion and basically remove it from that 3D lattice like that. Are we okay with that so far? The reason why I'm drawing an image is that they often ask you to draw on the exams, and even though it doesn't state, like it says on the exam script, like optional, it's usually part of the excellence criteria. So, and then for this negative ion here, we're going to get the other direction of the water molecule because you want the positive side. So you see how I'm drawing it in the other direction? That's the slightly positive. So when that guy gets isolated out, ooh, hear the rain. It looks like that. So still same rules apply, positive and negative attract. Opposites attract. Are we good? Taking pictures of it. I am going to scan it and put it online. Don't worry. All right. Are we okay with that as an idea? Yes? Okay. So talking about that practical you guys did the other day. Yes. Bathroom as well. Okay. I don't know if you want to go out right now. Huh? Yeah, but you're going to get wet. That's my bigger concern. All right. So are we okay with that as ideas? All right. Can I talk about the experiments you guys did last week? Not last week, the week before. So do you guys remember about electrical conductivity? The experiment where you guys tested electrical conductivity. All right. When you guys did water by itself, was water conductive?
Yes.
No. Water on its own wasn't conductive. So if we think about the water molecule does have a slight negative and a slight positive end. But if we look back at our notes from last week, it said to be electrically conductive, there needs to be a mobile, free to move, charged particles, either electrons or ions. This is not an electron or an ion. Even though it is charged, the charge is only slight. So water on its own won't be conductive. So that's why you saw that that wasn't conductive. When you guys did pure salt, was that conductive?
Yes.
Pure salt by itself? No. And that is because, again, looking at that definition, it needs to, so even though this has ions, which fits one of the two criteria, electrons or ions, it was not mobile. It was not free to move. It was set in a 3D lattice. So the only instance where the ionic solid will be electrically conductive is if it's dissolved in water, because once it's dissolved in water, they are free to move. So that's one instance. The other instance is if you melt it. So you got to melt it with a Bunsen burner, and once it's melted, then it will be able to move those ions around. So it's a very common question on the exam, why are ions conductive in this state but not in that state? It has to do with the fact of, is it locked in a lattice? Are we okay with that so far? All right, let me know if you want me to write something down. I'm trying to keep the notes short. All right, the other thing that we talked about was solubility. So when we looked at dissolving salt in water, was that soluble? Did it break apart? And you shook it. Salt in water. Yes. Was it soluble in oil? Sort of, not really. It basically wasn't. So that was oil. And then with ethanol, was it soluble? Ethanol. Sparingly soluble. So some things to keep in mind. When we talked about ethanol, and I did write this on the board for some people because we were asking questions about that. So this was ethanol. And if you guys remember, there was some solubility with ethanol. It wasn't a whole lot. So ethanol does have some solubility. It is slightly negative where the oxygen is. It is then slightly positive on the hydrogen, but it's not as greatly polar as compared to water, because you have this tail here that's basically nonpolar. So when we're talking about something that is nonpolar, we're talking about something that doesn't have charge. So nonpolar, no slight charge. So if I don't have any charge, I won't be able to attract any of the ionic solids because I won't be able to pull those ions out. There's nothing to attract to it. So this guy here was sparingly soluble because there was a little bit of a charge, but it wasn't as dramatic as the water. So that's why you saw kind of a continuum. Are we okay with that so far? Questions, concerns, comments? All right. One of the things that we did talk about last year with the precipitation reactions was why some ionic solids do not dissolve in water, and that has to do with the force of attraction. And we'll learn about this more in our next internal. So if something is soluble in water, the attraction to the water is greater than the attraction to itself. If an ionic solid is not soluble in water, the attraction to itself is greater than the attraction to the water. But I'm not going to write that down because I don't want to confuse you guys. When you guys are doing this standard, all the ionic solids they should give you would be soluble. Okay? So you can assume just that one characteristic. When we do when we do ion identifications, then we need to know the difference. Cool. All right. Questions, concerns, comments. Does that hopefully fill in some of the gaps from your learning? All right. So one of the things I want to pass on, because we're now ready to move on to the next step, is yes. It doesn't work. I don't think it works. It just didn't work. It worked for you. It doesn't work for everyone. All right. So level 2 chem. One last thing, and then you guys have time to work. So I think you guys are ready to move on to some of the NCA style questions. You have done some of the SciPad pages, so you are ready to kind of move on to the next step, and this is the next step. I have specifically just chosen questions that have metallic solids and ionic solids. So you are going to be tested on all 4, but we've only gotten to the first 2, and that's why I've only selected these ones. In fact, we aren't going to pick up the other 2 until the end of our last thing we learn, basically. So that's why I just wanted to show you guys these 2. It just gives you a chance to kind of see how they ask the question in the exams. With these questions, I have put these tables back in. I know you guys have already done these, but it's a good refresher because you need to know particles and forces to be able to justify the properties that are occurring. So you have things like this one here talking about solubility. You have this one here talking about conductivity and ductility. This one here is malleability and brittle. This one here looks at solubility again. This one here, I'm sorry that the thing doesn't look as great, is malleable. And then this last one here is conductivity and solubility. And again, you see the zinc and the zinc chloride. So just to give you guys some ideas of what these questions look like, I have put the marking schedules on my Google site, but I just want to kind of show you where it is because it's not in an obvious spot in case you want to check your answers. So lesson number 3 under ionic. So I've done the collated metallic solids and ionic solids questions just so you guys can have a chance to look at it. The answers are going to lead to a folder. So NZQA unfortunately has taken down not all of them, most of the exam scripts from previous years. They only show the last 3. And I thought that was kind of stink because you actually need more than 3. So I have saved all the exams that were there before they took them down, so that way we still have them. This one here is the exam paper. These ones here, ASS, is going to be is that the assessment? I think that's the marking schedule. Just click it to make sure. You know, open. Is the internet playing up again? I need to download it? That's annoying. Okay. There we go. Yes. So it is the ASS one. So these are the assessment schedules. So what you need to be mindful of when you want to check your answers is that I have noted which exam it is. So 2022 exam, question 3A, and you can then look up the marking schedule on there, which has now disappeared. Where'd you go? There you go. Nope. Internet's being buggy today. No. Oh, wait, there it is. So you can actually look and check your answers that way. You can see how, again, how they have broken down the achieve, merit, and excellence. Be mindful with a lot of this. The achieve level is just the identification, so stating what you know property-wise and the structure-wise. Oh, wait, that's not the right one. There we go. So it describes the structure, identifies that the mobile charged particle. The merit is explaining why, so looking at the property and linking in, so using words like because and therefore. Excellence is that comprehensive explanation. A lot of what excellence is getting both. Getting both of them. The other thing that they often look for the excellence is that compare and contrast. You see how in this case here, fully justifies solubility with lithium bromide and use of a diagram to answer, but when you actually look at the question, oh no, this one actually does say the use of a diagram is required, so that helps you out. But I have seen instances where they just say you may include a diagram, and then they actually did mark you for the diagram. So always draw a diagram. Cool? All right, questions, concerns, comments? All right, so the other thing I want to give you guys a heads up on so you're aware is that I'm going to give you guys Thursday as a study day just to get used to the NCA questions. And then on Friday, what I'm going to do is give you guys a CPR quiz. It's kind of like an open book quiz. I'll explain more of it on Friday, but just be mindful I'm going to give you an exam question to do. Cool. That's us. Sorry I talked for so long.